to start the lecture today. We'll continue on the PMSM machine drive. In the last lecture, we come up to that we have the analytical model of the machine, and then we are now ready to develop the control. So I'll have a little bit repeat from the last lecture, and then I'll focus on this lecture today. So what we see in the last lecture, just feel free to interrupt me if you have any question in somewhere. And what we see in the last lecture, we have developed the equation for the torque. So we have the torque equation, and it's become like this. And what we see, this is we have the magnetic flux, and then we have the stator current, and also this is an angle, and this angle is the angle between the q-axis and the stator current. And also you have the second term, and what we see, we have the magnetic flux, which is constant, and we have here a stator current, and we have the stator current angle here, pole wheel angle. And what you see that if you keep this current constant, a stator current constant, then only variable here we have is the pole wheel angle. This is stator current angle. So we need to decide where to place, how to find this angle that gives us the maximum torque. And if we plot this equation, this torque equation, with respect to this angle, and it becomes like this one. So what we see here, this is the first quadrant, and this is the second quadrant. Here, this is a zero angle, and we have the plus angle and the minus, and this is the pole wheel angle. This PP, and from this you can see that for which angle we can get the maximum torque. So, for example, when you have the current 0.2 per unit, and for this we see this is the plot for changing of the angle, and we see that at this point we get the maximum torque. So for this current we get the maximum torque when we set this angle here, this degree, something like 20. And if you increase the current, like for example, when it's 1 per unit current, then you can get the maximum torque, something like this, and the angle is somewhere here, close to 35 degrees. So we see that based on this angle, we can decide, you can have the maximum torque from the PMSM machine. So this is one way of representation, and another way of representation of the torque is like this equation. And here, this angle is the stator flux position. It gives a stator flux position. And if you look at stator flux position, how it look like, we have the d-axis, and we have the q-axis, and this is the stator flux here, CS, we can say. And here, this is the angle, epsilon, CS, R. So one way representation torque like this, and the second way we can represent the torque in terms of the flux, stator flux equation. And we see that if we have the if we keep the stator flux constant, then only the position that gives us the maximum torque. So this is the position, and it tells us how we can get the maximum torque for the same flux with a different angle. So this is the same thing, like if we set the angle somewhere here, then it gives us the maximum torque at this point for this amount of stator flux. So based on this knowledge, we can develop the control for the PMSM machine. And we usually have two different control. One is called cos P control, and another is psi P control. I'll discuss these two control. Before that, I want to say about this synchronous machine, because you work a lot with the permanent magnet synchronous machine, when you have this field current, when you can change this field current to have this flux, to change this flux, and you can change the torque by changing this current here in the permanent magnet machine. But in the synchronous machine, where we have the separate excited magnet, But in permanent magnet, we have this fixed. So we cannot change this part. So we only can change only the current, this IQ, and the ID. So we need to define how we can find this IQ current reference and the ID current reference based on the torque that we want to have. So two controls that we are talking about. So this is the two control that we are talking about. The first control is the cos P is 1. Here cos P is the angle between the current and the voltage. If you remember the phasor diagram, how it looked like, we have the Q axis here and we have the D axis. And this is the voltage, stator voltage, and we have the stator current here. And this is IS, and this is the angle here. This angle. So this is the angle between the stator voltage and the stator current. And what we are doing, we are placing the current in the same axis as the voltage. That gives us the cos P is equals to 1. This means power factor 1. So if we have the power factor 1, what is the advantage that we can see that since we have the converter that is supplying the current to the machine, we have the converter, and this is the output of the converter here. And if cos P1, this means power factor 1. If power factor 1, this means we don't need to, we have the minimum losses in the system. This means we are sending minimum current. The losses in the system, which is I square RS. So when it's power factor 1, then we are providing minimum current to produce the torque that we want in the system from the machine. That gives us the minimum loss. Earlier, in 1970s, we tried to send minimum current through the converter because the semiconductor is very expensive in the converter. So if we have a larger converter that can transfer more current, this means we are increasing the cost of the converter. But nowadays, the cost of the converter is not that much. So we have an alternate control. But first, I also want to discuss a bit more detail how this control work here. So what we see here, we have this Q axis here. So this is the Q axis. And if you look at the D axis, and D axis is somewhere here. And this is the D axis. And what we see, we have the voltage and the current. We place them both in the same axis. If we place them both in the same axis, then we have a magnetic flux here. This is the magnetic flux. Only this part, not N, here. So we have this magnetic flux here, Cm, and this vector and Cm always placed in the Q axis. So we have this vector always placed in the Q axis, and we have this vector here is 90 degrees with respect to the stator current here, stator voltage. So we got this figure here, this phasor diagram. And here what we see, we have the current here and also voltage. And we have this part. And then we have this another vector for the magnetic flux here. And now we see that this angle here is 90 degrees. And this is the angle, delta, and it is the angle between the Q axis and the voltage vector. So from this, what we can see, we can write this cos delta. This cos delta, according to the Pythagoras definition, which is US. This is the US vector. And here, this vector here. So this is the according to definition, we got the cos delta. And then according to Pythagoras, we can write again this UP, this vector, which is the square of this vector and this voltage vector. So that gives us this equation is according to Pythagoras. A square of this plus a square of this equal to the square of this. So that's how we got this equation. And in that, we say that UP, which is defined as n psi m, because this part here is psi m. So we have n psi m, which is equals to, and US, and you can see that US is n psi s. And then you can write US is equals to n psi s there, n psi s square, plus, and then you have n xs is square here. And if you rearrange that equation, you will get this equation. From this, if you rearrange, then you are getting a stator flux equation. Since you have n square inside and n square inside, and if we take the n out from here, and then it cancels with this n, and if you rearrange this equation, then you can write this stator flux equation, which is equals to this equation. So what it's saying us? It's saying us the stator flux, this psi s, it also depends on this current. This means if you increase the current, which is reducing the stator flux, right? Since this is minus here, this means if you increase the stator current, this means it's reducing the stator flux there. So this is the one observation that we notice. And then in the second one, we want to see what is the relation with the torque with the current. And then you can see that here we have the torque. And according to the torque definition, we find that is the psi m multiplied with the q-axis current. And this q-axis current, we can write the q-axis current has a two current component. One is this current. This is the IQ. And another is, this is ID current. And if you write the IQ, and you have the angle here, this is the angle, right? Delta, you can say here, we have the angle delta now, because both the US and IS in the same position. So that you can write IQ is equals to IS cos of delta. So you can write IS is equals to cos of delta. Now again, I want to replace this equation with some part like the stator flux, this magnetic flux. From this you can see that n psi m, this one giving us UP, n psi m give us UP, then you can write psi m is equals to UP divided by n. So that's what we wrote here, UP divided by n. And then you have the IS, and you have the cos delta. And according to definition from this Pythagoras definition, you can write the cos delta, which is this vector divided by this. So you have this vector, which is US, and divided by this, which is UP. So now you got US divided by UP, these three terms. Psi m, this gives us this, and you have the IS and cos of delta, we can write this. And if you simplify that, what you can see, you can write, you can cancel this part UP with UP. You can cancel this part, and then finally what you have, US over N and then IS. And we know that from this definition, US over N give us psi s. From this we are getting US over N give us the stator flux. So that we can write the stator flux here. So this term we can write the stator flux and then a stator current. So now we can represent the torque in terms of the stator flux and the stator current. So from this equation, what we see, if we increase the current, stator current, it should increase the torque, right? What do you say? You are increasing the stator current, then it should increase the torque. Again, one definition, we need to look at this flux equation, and this is the flux equation. And if you increase the current, it increasing the torque here, but again, it is increasing the stator flux, decreasing the stator flux, because this is a negative sign here. So what we see that if you increase this current, then it will increase the torque. At certain point, since there is a minus sign, torque should reduce. And if we plot it, then how it look like this here, this curve. So this is the torque you have, and you have the current, stator current, and what you see, you are increasing the stator current, that increasing the torque. It's increasing the torque, certain point, and when it reaches somewhere at the peak, then even you are increasing the stator current, it's not able to increase the torque anymore. This is the control topology that I think you use in the synchronous machine in the last few lecture with Roy. And here is because we are not able to control the field current. If we are able to field current, then it should not reduce, it should go up. But since we are not able to control the field current, so it's reducing. And this is not an optimum control for PMSM machine. But this control only used earlier because we want to have the power factor, unity power factor, to reduce the current flowing through the converter, because the converter is very expensive. But nowadays, converter is not that expensive as before, so we want to have an alternate control. And this control called PP control. PP is, equals to 0. Is this control, this angle here. And if you remember, what is this angle? If you look at again the phasor diagram, and we have the q-axis, and we have the d-axis, and we have this US, and we have this IS, and this is the angle here, PP. This is the angle between q-axis and the current, and the stator current. So in this control, what we are doing, we are making this current angle to 0. So if you want to make this angle to 0, then what are you doing? You are shifting this stator current towards the q-axis. So that is what you see. We have the stator current is on the q-axis. This means we make this angle to 0. So we have the q-axis here. This is q-axis. And then you will have the d-axis somewhere here. Now we have the current, stator current, which is the stator current here. This is stator current, IS, is now with q-axis. So this is q-axis. Now we have also this angle, delta. This is the angle between the q-axis and the US stator voltage. So we have this. And then we know that this vector and is perpendicular to this current. So we have this 90 degree here. And then we have this trigonometry here. Then we can apply the same Pythagoras. So if you apply the Pythagoras, what you see here? We have this 90 degree. This is 90 degree, and we have this delta angle here. And then what you see? So this voltage, we define same as UP, and this part, Cm, and it is N time Cm there. And here we have the voltage US, and we have another vector here, N XX IS. So if you look at the Pythagoras for this one, what do you see? Yeah, first part we define this EP, and then you have US. So from this equation, you can write this US, which is N psi S. So these two you got from the definition. Like from here, we got this part. And then we define UP is equals to N psi P. So from this Pythagoras, then we can write US square, which is equals to N psi M square plus n excess is square. Right? This is according to Pythagoras that we can write for this. This square equals to this square here is NCM square, and then this one square. So according to Pythagoras definition, we got that. And then again, we have this US, which is n psi s. So it's n psi s square here. And from this, you can write psi s is equals to this equation. Right? So you got a stator flux equation from this. And then what we see that now if we increase the current, and now this is the plus sign here. Before we see that was minus, and that time when you increase the current, and we see that this flux is decreasing. But now if we increase this current, the flux is also increasing. So that's one good point. And I'll discuss why this flux is important in torque producing, why you don't want this flux reduced and that bring low torque. So this is the one that we see when it's the current increasing, this stator flux increasing. And now if we look at the torque, and we see that torque, which is magnetic flux, multiply with IS, stator current. And why is stator current? Because all the current now in the q-axis. So all the current now in the q-axis, therefore you can write IQ is equals to IS here. Because we do not have, what is the d-axis current component? What do you see here? D-axis current component? Since the stator current now aligned with the q-axis, so all the current now in the q-axis. So there is no current in the d-axis. So d-axis current is now 0 there. So since the axis current is 0, then we can write IQ is equals to IS. So what it was saying now, the torque from this equation, it was saying that torque is now proportional to current. Since it's the magnetic flux, which is constant, and is the current, stator current. So this means I see a linear relationship. This means if you increase the current, and it will increase the torque. Now if you plot also this, and you will see here, you increase the current, then it will increase the torque. You have the torque equation and the current here. So is the PP is equals to 0 control, the second control. This one is the unity power factor control, and this one is the PP is equals to 0 control. And what we see that, if we increase the current, then it will increase the torque. So this is the optimum control for PMSM machine. And we will investigate this one further, this control topology for the PMSM machine. Any question here after this? Yeah, just feel free to interrupt me if you have any question. Yeah, this is what we see in the first unity power factor one. This is the unity power factor. And what we see that when you increase the stator current, then it's increased, it always decreases the stator flux. So that's what we see. Because if you remember the equation that we see for this one, which is Cs is Cm square minus XS Is square. So this is the equation for the unity power factor control. Therefore, stator flux is decreasing here. And the other one, what we see, Cs is equals to Cm square XS Is. And therefore, you see that when it's increasing the stator current, then it's increasing the stator flux. So we want to investigate the control further, this PP control. And that is the optimum control for permanent magnet machine. And in that, we want to look at some of the equation. For example, we see that stator current vector that we can represent it like this. When we neglect the losses across the stator resistor, we are assuming that the stator resistor is 0. It's actually 2-3% of the system resistor, but we can neglect when we develop the control. So therefore, we can write a simplified equation like this. And then we can write the stator flux linkage. This is the total stator flux, which is the magnet flux, and the flux linkage because of the current through the stator. And this is the total stator flux. And if you write separate equation for d-axis and the q-axis stator flux, then we see that we have the d-axis flux. Q-axis flux, this one is only depend on the current. And the d-axis flux is this one. And it's because we don't have anything in the q-axis from the magnet, because psi m is always in the d-axis. So the psi m we define such a way that it always stays in the d-axis. So therefore, we don't have anything from psi m here in the q-axis. So we have this, and then we have torque equation. And we see that torque, it produces maximum torque when we place the current vector in the q-axis. When we have the current here, and we have the CM here, and we have the 90-degree angle at this, that produces the maximum torque. I want to give you one numerical example. In the last lecture, I said that I'll try to include some numerical example. For example, we are considering one machine which has the stator reactance XS, let's say 0.3 per unit. And the magnetic flux, Cm, we say it has 0.66 per unit. They're in per unit, Pu. And then we assume that stator voltage, max, you can say this is max, could be 1 per unit. And we want to have torque, which is 0.5 per unit. That the torque that we want, is the reference torque, we can say. That's what we want. And we want the speed of the machine, 1.2 per unit. So we want to look at the machine condition. And one thing, first we can say that the maximum stator flux linkage. And stator flux linkage max is the US max divided by speed. So when it's low speed, like if its speed is 0.1 and US max is 1, then it's 10. So you have a lot of flux, stator flux. So we don't need to worry about if we are assuming that, if we neglect the magnetic saturation, then you got a lot of stator flux. But here we want to have the higher speed. So we said that we want to have the speed, which is 1.2 per unit speed. And then that gives us the magnetic flux, which is 0.8929 per unit. So this is the magnetic flux, stator flux max that we can obtain. So we have the torque equation. And torque equation, which we know, Cm, IQ. And from this, we can write IQ, which is torque, divided by Cm. And we say that we want to have the torque 0.5 per unit. And we have the Cm, which is 0.66 per unit. That gives us the Q-axis current, which is 0.7576. This per unit Q-axis current that you can get. So now we can see Q-axis stator flux, CQ, which is xs iq, and we have the xx 0.3, then we multiply it also with iq, that give us 0.2273 per unit. So this is the QXS flux that we obtain. And what would be the DXS flux? Psi d, and we know that psi d, which is xs id plus Cm. And one thing from the equation, we know that only the Q-axis component gives the torque, not the d-axis. So we try to put the d-axis current to 0. That's what we want to have. So we put the d-axis current to 0 there. If the d-axis current 0, then we got the psi d, which is the same as the psi m, 0.66. And now, if you calculate the stator flux, psi s, which is psi d square plus psi square root of psi q square. And that gives you 0.698 pu. So here, what I want to highlight, to get this torque with that speed, and we see that the stator flux, maximum stator flux can be 0.8929. But after calculation, we see that we got the maximum flux, which is 0.698. This means this one is less than this. So this means the machine can operate without any problem, because we have the flux linkage which is less than the actual one. This means we can increase the torque to get to have more, we can increase the Q-axis current to have more torque from this machine, because this flux is less than maximum stator flux. But I also want to show you one example where we have where we need to do the field weakening. For example, same case. Now I want to increase the speed of the machine. Like here we have the speed 1.2. Now I want to say that I want to have the speed 1.5 per unit. If we want to have the speed 1.5 per unit, then what would be the maximum flux linkage, maximum stator flux? And we have the 1, US max, and now N, which is 1.5. And that gives us 0.6667 per unit. So this could be maximum stator flux that it can be. So this can be maximum stator flux. From the previous one, we see that stator flux can be maximum. This could be the maximum flux in the stator if we want to have the same torque with this speed. But we see that stator flux here for this operation, it would be 0.698 per unit. This means the converter cannot supply, we cannot supply this amount of flux, stator flux in the machine. So if we cannot supply this amount of flux, then what we can do? So when you cannot supply this flux, then we need to do field weakening. This is called the field weakening. So how we can do the field weakening? Then we can check the maximum flux, the remaining flux that we have here. So we see that we have the some Q-axis flux that we calculated here. This is the Q-axis flux for torque production that we need. From this, you can see the remaining d-axis flux that we can have, which is psi s max minus psi q, here square. So we have the psi x max from here, and we have the psi q from here. If we insert these two, then you get psi d which is 0.6268. So we say that we can have psi d maximum this value to get the same torque. So what we do field weakening, and if you remember the equation for psi d, which is xs id plus psi m. And then we need to calculate the ID current from here, which is psi d minus psi m over xs. And if we insert this value there, we have psi d, and we also know psi q, and we have the value also psi s. If we insert all of them, and you will see that we got the sum current, and this current is 0.1107. So we need to have this amount of current, negative d-axis current, to operate the machine at the speed that we want. So we are providing some negative current, and because of this negative current, what is happening in this equation? What is happening here in the psi d? We are reducing the magnetic stator flux. This means now we need to provide some negative current that makes this smaller. So, and this method is called field weakening. So we are weakening the field so that we can operate the machine at the torque that we want, at the speed we want. So the calculation here I have done, we can put it, when we can put it in the software. When we program it, the control, then we put something this way, the calculation inside the software, so that it calculates automatically how much the d-axis current that we can provide. So we need to have the main target about the d-axis current. And one thing we also need to look at here, we cannot have the current maximum more than 1 per unit. This means stator current IS should not be higher than 1 per unit. This means ID square plus IQ square, it should be less than equal 1 per unit. So what we see here, we have this stator current, which is minus the d-axis current plus, and we have the q-axis current that we calculated, which is 0.7576, and it gives us something like 0.7656. So we got the stator current, which is less than 1. This means we can have this operation after applying field weakening algorithm here. So any question here, how we can apply the field weakening to operate at the desired speed? If any question? So what we see that we can do, we can apply the field weakening when we need to, because we have the US, we have the current, we have the voltage, stator voltage, which is fixed because we have the converter, and converter cannot supply more than rated voltage. So we have the fixed voltage. If we have the fixed voltage, and then from this equation, and we see that psi s, this stator flux, which is limited by the stator voltage that we can apply from the converter. And sometimes we see that in order to supply that desired torque with a desired speed, we need to do some field weakening, and how we can do the field weakening after supplying negative d-axis current. So this is the only component that you can see that if we want to do the field weakening, either by reducing the psi-d component or the psi-q component. And if you want to reduce the psi-q component, this means it's only the q component that you can, q component of the current that need to reduce, and we don't want that. Why you don't want that? Because if you reduce the q-axis component of the current, this means you are reducing the torque. So you don't want to reduce the torque. Therefore, this is fixed, and we don't want to reduce this q-axis current. And only one way here to reduce the d-axis current. This means supply a negative d-axis current. So the optimum is to provide the d-axis current to 0. If not, if we need to do field weakening, then we will provide some negative d-axis current that give us the field weakening. And how much the field weakening we can do, it depends on how much torque you want to apply. For example, you can apply, if you want to have very high speed, then you can apply all the current for the field weakening. Then if you apply the whole current for the field weakening, then you have nothing left for the torque production. So even though you are going very high speed, you can running the machine with a very high speed, but you have nothing to do produce any torque. So that's what also we don't want. I'll show you one example here. So what do you see? This is the speed, and this is the torque, and also the flux here, torques and flux. And what do you see? If you are increasing, and after this speed, there is operate normally up to here. Is the 1 per unit, let's say, speed. And the stator flux, that's okay. And then if you want to increase the speed of the machine, it's 1 per unit speed. And if you want to increase the speed, then you need to apply the field weakening. So if you apply the field weakening, and what is happening? Torque is reducing. So we don't want this action. Yeah, sometimes it's okay for this machine, and then but here for this one we see that if we apply the field weakening, then the speed is reducing. And here at this point, it can reach up to 1.5 per unit speed, but there is no torque here. This means if you apply any load at this speed, then machine will not run, because there is no energy to run the machine with the load, because you apply all the current for the field weakening. So this is the first step, and this one is for the surface-mounted machine. And for the surface-mounted machine, what we see that if we increase the speed, then because of this field weakening, and it cannot supply any torque. So therefore, for example, in traction or electrical vehicle, we don't use this surface-mounted machine, because this d-axis current we are applying for the field weakening is only increasing the speed, but it's not supplying any torque. So we don't use surface-mounted machine for EV or traction or all these things. And if we look at the interior-mounted machine, and you will see that this torque characteristics will be different. It would be like something like this. So we'll also discuss this for the interior-mounted machine, and you will see that even though you are doing the field weakening, but you will have still some torque left to run the load. And this will be for interior mounted machine, and this one is for the surface mounted machine. Yeah, I'll discuss how we implement the software, this part, in the next lecture. I think we don't have that much time. So yeah, we have some time for if you have any question. We can take some question before break. So if you have any question, you can also discuss during the break. Now, yeah. So now is the time for us to have 15 minutes break. Then you can start the lecture after the break.